At Aerzen, since 1864, we design high-performance blowers, screw compressors, and high-speed turbo blowers for the industry. We introduced Europe's first positive displacement blower back in 1868. Since then, we have become a global player with over 50 subsidiaries around the world and more than 2,500 employees. Our goal is to redefine quality and innovation, so when you see an Aerzen name on a machine, you know exactly what you can get. You can expect performance. Hello, I am David Salazar, Aerzen Regional Application Manager for Pneumatic Conveying Applications. Welcome to this interactive presentation, which is meant for you and me to participate and learn from some real case scenarios related to energy, CO2, and cost reductions in the pyro processing for cement manufacturing. We're glad you've decided to join us in today's presentation. If you are willing to learn more about other applications or Aerzen services for the cement industry, you can also take a look to our specific application content in our YouTube channel. The case scenario we will be discussing today develops in a real cement plant, where Aerzen has been supporting different needs in after-sales and basic engineering advisory for the past 10 years, building a professional, strong, and trustfulness relationship that have granted Aerzen team to get involved in several renovation, expansion, and optimization projects over the past years. In order to have a better view of the topics we will be discussing today, here you can see the technical data from the plant. Cement industry, as mainly all other industries, require a raw mix to produce the final product, clinker, which is basically finished cement before it's grinded in the final milling process. Raw materials quality and the proper chemical composition of those materials are key factors to guarantee a proper burning process, avoiding lower heat transfer to bad quality batches. Raw material is as important as everything else in the process and play a critical role in the final product quality. Cement is manufactured through a closely controlled chemical combination of calcium, silicon, aluminum, iron, and other ingredients. Can you tell what is the composition range for a good quality mixture of Portland cement? Let's see the options. If you selected option B, you are correct. Raw mix for cement production needs to have a majority composition of calcium oxide and silica, and a lower proportion of aluminum and iron components. The percentage by weight included in the original mix is tested in the laboratory and needs to fulfill the ASTM C1157 standard classification, so it can be called Portland cement. Any deviation in the composition range, it's a valid construction material, but cannot be called Portland cement, and in consequence cannot be used for highly strength concrete applications such as buildings, bridges, roads, and so on. If we take a closer look to the last two materials showed in the chart, we see that the amount of material is represented as a minimal possible quantity and not as a percentage per weight. The reason for that is basically because the more magnesium and potassium we have in our mix, the harder the oxidation process will be, and we will see incomplete chemical reactions and bad clinker quality. Avoiding these two elements may not be as easy as it seems, as they are attached to the original stone. Corrective materials needs to be added and properly mixed to correct this problem from the beginning. However, it's impossible to avoid having some rocks with extra content of these two materials, which makes the work harder for the raw material milling machine that won't be able to pulverize completely the rock that contain higher quantities of these materials. In our customer's plant location, raw material is found with the following characteristics. Do you think they can use this raw mix to produce Portland cement? Clearly, they can't, which means they need to add corrective materials to guarantee the chemical composition before the raw mix enter into the process. The materials used to correct the mix depend 100% on the local availability and will change from plant to plant, even if they are located in the same country. As inland transportation costs are a higher price to pay, cement plants will look closely for the nearest material available. In this specific case, they use kaolin and clay materials to add the expected minerals into the mix and overall reduce the amount of magnesium and potassium as arranged per weight in the mix to avoid major problems in the milling and burning process. All these materials needs to be properly mixed in the homogenizing silos, so the final composition is as smooth as possible and with the granular size needed to enter the preheater tower. Silos homogenizing and raw material pneumatic conveying to the preheater tower are two of the most important applications in a cement plant, where Aerzen equipment homogenize and convey millions of tons of raw material around the globe with our high-performing equipment. From the beginning of their operations, this plant uses a set of 10 Aerzen GM25S units to homogenize the mixture in 3 silos with a capacity of 12,000 tons. They had by the time a sliding vane compressor in operation to deliver pneumatically the raw material into the preheater tower. Operational conditions for those two processes are as follows. Late in 2017, a production increased demand required more raw material per hour for the process. As I mentioned, the existing machine was a rotary vane compressor that requires a fair amount of oil in its reservoir, a permanent water supply for cooling, and at least a year overhaul to guarantee the internal gap between the vanes and the cylinder to keep the same efficiency level. The machine was also operating near their operating capacity, and an upgrade wasn't that easy at the time. Aerzen team supported with the pre-engineering process and helped with basic calculation for the new pneumatic conveying capacity that the system required. The real challenge for this project was to increase the conveying rate from 2,700 kilograms per hour to the maximum capacity, maintaining the same piping system for the homogenized raw material. As mentioned before, for the type of material and density, the most common conveying method is dense phase, which basically means that the material travels at a slower speed, in general, lower than 20 meters per second, on the bottom of the pipe from one point to another. The pipe diameter was an important restriction to the project. However, by increasing the volume flow by 50% and the pressure capacity 15%, we were able to increase line conveying capacity from 2,700 kilograms per hour to 3,500 kilograms per hour. Conveying speed also has an increase as more material needed to be moved through the pipe with the same diameter. However, we managed to stay at the lower 19 meters per second to avoid pipe clogging. Let's review some of the major takeaways from this case scenario in which we replace the sliding vane compressor technology with the Aerzen Delta screw compressor. First, 29% material handle increase, keeping the same major elements as piping, electrical wiring, footprint, and no major civil or mechanical investments. Second, keeping the same energy consumption but increasing almost 30% the production capacity. And third, avoiding costly maintenance to oil reservoirs, water supply for cooling, and complete repairs to the sliding vane technology characteristics. Thanks for joining us today in our interactive presentation. We hope you have enjoyed our journey through one of the most exciting processes in the cement manufacturing. If you have any further questions, I'll be happy to discuss it with you later. And make sure to contact your Aerzen entity in your region for any specific questions or local support you need from our team. Thank you.
Expect performance.
Expect performance.
Expect performance.